Yo, yo, yo. What up, peeps? I'm here, dude in a room, Nick. I'm here to show you how to do exactly CS50, Harvard, Artificial Intelligence, Heredity Project, Project 2.x. There's two Project 2s. This is one of them. All right. Let's look just at what we're supposed to deliver. Our program gives us data about the GJB2 gene, which is a cause of hearing impairment. So trait is going to be hearing impaired, and gene is going to be a mutated version of the GJB2 gene. So when I say have the gene, what I mean is they have a mutated version of the GJB2 gene. But this could apply to anything. So the input is a CSV file with essentially 4 columns: name, mother, father, and trait. And as you can see, there is variation. Some people may not have mother or father listed. The trait may not be present, it may be present and true, and it may be present and false. Our final output, and this really is for family 0, what the real answer is, should look like this. So essentially a Python dictionary of dictionaries, and these are a probability distribution. These are going to sum up to 1. So how likely is the person to have 2 copies of the mutated gene? How likely is the person to have 1 copy of the mutated gene and 0 copies of the mutated gene? These sum up to 1. How likely is the person to have the trait and to not have the trait? And again, they'll sum up to 1. So that's the output. Okay, now I will download the project file, and I'm going to use VS Code to do this. So if you're not using VS Code, these next 2 steps may not apply, but bear with me because most of it will apply to you. So I'm just going to open that project folder. And we can see our family files here in the data directory and heredity.py. To run it, we need to pass the file as an argument. So what I do in VS Code is I just say debug using launch.json, and this will create launch.json. It'll crash. Boom. But importantly, it'll create launch.json. And I just am going to add 2 arguments to make it always run with a file. So cwd, current working directory, cache workspace folder, and then the args is going to be the name of the file. So I'm going to use family0.csv, but it is in data/family0.csv. Then quickly, after we load people in main, right here on line 45-ish, I'm just going to print those people to make sure it loads. And it does. There is our family in Python. What the main function of our program is doing is applying Bayesian inference over all the possible assignments of hidden variables. Then it is summing up or joining those probabilities to arrive at per person marginal probabilities. The program is modeling all possible worlds where each person might have 0, 1, or 2 copies of the gene and may or may not have the trait. It only considers worlds consistent with what we already know, the evidence, regarding who does or doesn't have the trait. For each world, it computes how likely that world is, the joint probability. It then adds the likelihood into the counts for each person's gene/trait buckets for that world. After accumulating across all worlds, for each person, we have raw weights, which we then normalize. On the right, I've shown which have trait combinations pass and fail the evidence for family 0. For this assignment, this outer loop is already given. Our first major task is going to be the joint probability function. The joint probability function should take as input a dictionary of people, along with data about who has how many copies of each of the genes and who exhibits the trait. The function should return the joint probability of all those events taking place. So the 4 parameters are people, 1 gene, 2 genes, and have trait. And these 3 are all sets of names. We're going to need this probs dictionary, as well as information about how mothers and fathers pass on the genes to their children. Here's the probs dictionary, and we can see it has 3 things: gene, trait, and mutation. Gene is the unconditional probabilities for having the gene. In other words, this is the probability distribution. If we don't know anything about your parents, your likelihood to have 2, 1, or 0 copies of the gene. Trait is going to be how likely the person is to have the trait given 2, 1, or 0 copies of the gene. And then mutation is going to be when the parent passes the gene to the child, there is a 1% chance that, for example, the bad gene becomes the good gene, or vice versa. When we do have information about the person's parents, we have the following. If the parent has 0 copies of the gene, there's a 0% chance to pass the gene to the child. If they have 1 copy of the gene, there's a 50% chance to pass the gene to a child. And if they have 2 copies of the gene, there's a 100% chance to pass the gene to their child. However, we also take into consideration the probability of mutation. All right, let's just dive in. Joint probability. If you read the hint, you'll see that we can multiply together all of these probabilities to get the joint probability. So the structure can be something like result equals 1. We'll do all our multiplying and then return result. And these are for all people. So we're going to do for person in people. And this is a bit tricky, but each time we want to multiply by 2 things. What I'll call the gene likelihood and then the trait likelihood. So I'm just going to call it gene P, and I'll just set it to 1 for now, and then trait P equals 1. And every time we do this loop, I'm going to say result times equals gene P times trait P. All right, to make it more readable, I'm going to add a couple of helper variables so we don't need to repeat ourselves. The number of genes is going to be either 0, 1, or 2. I'll just say 0. So if person in 2 genes, num genes equals 2. Elif person in 1 gene, num genes equals 1. Then I also want to know if the person has the trait, and we're just going to use that have trait set. So has trait equals person in have trait. We're definitely going to be interested in the mother and the father. So I'm going to say mother equals people, person, mother, and father equals people, person, father. And I just want to know if this person has parents. So I'm just going to say has parents equals mother and father. And now trait P, we pretty much can fill it in using the probs dictionary. So I'm just going to say this equals to probs trait, and then num genes, and then has trait. For the world where we have 0 copies of the gene, the probability of this world is the same as the probability that no parent has passed us a copy of the gene. For the world where we have 1 copy of the gene, the probability of this world is the same as the probability that exactly 1 parent passed us the gene. It could be the mother and not the father, or it could be the father and not the mother. The two are mutually exclusive, so we can add the 2 probabilities together. For the world where we have 2 copies of the gene, the probability of this world is the same as the probability that both parents have passed us the mutated gene. Using this information, we can make a helper function to give the likelihood of a person passing on their gene. And we'll also consider the chance of a random mutation. So let's go. Def pass gene probability for a person. And I'm going to use these same 1 gene, 2 gene arguments. So if the person is in 2 genes, we're going to return 1 minus probs mutation. In other words, 100% chance. Elif person in 1 gene. We could do 0.5 plus mutation and 0.5 minus mutation, but they're going to turn out to be symmetrical. So we can just say return 0.5 right here. And finally, if the person, or with no copies of the gene, there's a 0% chance. Again, with the chance of mutation. So this is just return probs mutation. Okay, now we have what we need to fill in gene P, and this one is a bit harder. So we've got two cases to consider. Number one is if has parents, and I'll just pass there for now. Else, we're going to use the unconditional probability for having the gene. So gene P equals probs gene and num genes. In the has parents case, we need to consider if the gene, the num genes is 2, 1, or 0. So if num genes is 2, one thing, elif num genes is 1, something, else something. And to fill these in, we can use our pass gene probability function to figure out the likelihood that the mother will pass on her gene and the father will pass on his gene. So I'm going to say mother P equals pass gene probability for mother with 1 gene and 2 genes. And then father P equals pass gene probability for father with 1 gene and 2 genes. So if the number of genes is 2, this means the mutated gene was passed from both parents. In other words, gene P equals mother P times father P. And in the last case, this means number of genes is 0. The mutated gene was passed from neither parent. So gene P is the inverse of these two probabilities multiplied together. So 1 minus mother P times 1 minus father P. When the number of genes is 1, let's remember we've got to add those two probabilities together. The probability that only the mother passes and only the father passes. So the mutated gene was passed from the father only. So I'm going to call this left-hand side. And that's going to be 1 minus mother P times father P. And then the other half of this, the mutated gene was passed from the mother only. So right-hand side equals mother P times 1 minus father P. And then finally, gene P is left-hand side plus right-hand side. Awesome. If you're still here, awesome, because the hard part is over. This next function, update, adds a new joint distribution probability to the existing probability distribution in probabilities. Yada, yada, yada. For each person in probabilities, the function should update the probabilities person gene distribution and probabilities person trait distribution by adding p to the appropriate value in each distribution. All other values should be left unchanged. So we're just gonna sum up the stuff that we calculated and add it into the appropriate slots. So for person and probabilities, if person in 2 genes, probabilities for person gene 2 plus equals p, and then we need the cases for 1 and 0. So L if blah, else blah, but I've got to be a bit careful because this is going to be for 1 gene, and these are 2, 1, and 0. Now, very similarly, we're going to do trait. So if person in have trait, then probabilities for said person of trait for true plus equals p, and otherwise they don't have the trait, so we say the trait is false. Actually, these should be plus equals, not equals equals. Finally, we'll need our normalize function, and this is just going to make everything sum up to 1. So let's do it. Normalize probabilities. We can again do for person and probabilities. And then I'm going to be reusing this same value. So I'm just going to make sum genes equals 0 and sum genes plus equals for 2, 1, and 0, 2, 1, 0, and then sum traits equals 0, and I'll just copy this one, sum traits plus equals that, and then same for false. And then I'm going to say if some genes is greater than some small epsilon, we're going to divide these by the sum. So that one divided by equals some genes. Same for 2, 1, and 0. And then if some traits is greater than said epsilon, we're going to divide these by some traits for both true and false. And that's pretty much it. Hit that like and subscribe. This is the correct answer. There is no coding mistake in the video. So you, my friend, have a most blessed of days. Thank you.